Have you ever wondered how a tiny, super cheap microchip, like the one sitting inside your microwave or maybe your car, manages to do incredibly complex math without, actually having a dedicated calculator inside? I mean, how does it crunch all those tricky fractional numbers when its hardware literally only understands whole integers? Well, the answer lies in one of the absolute cleverest engineering tricks in computer science.
Welcome to this explainer. I am so excited to guide you through this today. We're going to pop the hood on embedded systems and see exactly how these device processors handle high-level math. We'll be taking some raw architectural concepts and seeing how they translate into these amazing, kind of hidden mechanical tricks.
Okay, let's dive into this. Here's our roadmap for today. 1. The cost of math. 2. The fixed point mindset. 3. Representing numbers in binary. 4. Multiplication and scaling. And 5. The rounding problem.
Right into Section 1, the cost of math. Why embedded systems skip the FPU.
So the hardware constraint we're dealing with here is pretty obvious. Floating point units, or FPUs, are fantastic for precision, sure, but they are absolute hardware divas. They have high latency, they demand a massive amount of silicon area, and they are incredibly power-hungry. On the flip side, your standard integer multipliers, they're lean, resource-efficient, and they basically come standard on almost every basic microcontroller out there.
So why exactly do we avoid floating-point hardware in embedded systems? Well, silicon area literally equates to manufacturing cost. And when you're manufacturing, say, 1 million microwaves, saving 50 cents on a microchip by dropping that FPU is a massive deal. Plus, power consumption drains batteries in portable devices, and latency just completely slows down real-time processing. Also, let's be totally honest here. Most everyday applications, like reading a basic temperature sensor, just don't require a massive dynamic range of numbers. Oh, and before you ask, yes, you could emulate floating-point math and software using the integer hardware. But doing so means calling these slow, emulating routines that just eat up your valuable processing cycles. Not ideal at all. Which brings us to Section 2, the fixed-point mindset. A clever hardware illusion. Enter the hero of our story, the fixed-point number. By definition, these are computations where the binary or decimal point is not represented explicitly in the hardware at all. The processor literally just sees raw bits, zeros and ones. Instead, the position of that point is tracked and known entirely by you, the programmer, writing the code. So whether it's a pure fractional number or a mix of integer and fractional bits, the hardware is completely oblivious to it. It's just doing integer math. Now, what's really interesting about this slide is this quote right here. Binary or decimal point is a state of mind for fixed-point arithmetic. It really is. There is no physical dot inside the chip. The dot exists only in your logic, in your scale factors, and in how you choose to interpret those raw ones and zeros. It's almost philosophical, right? Moving right along to Section 3, representing numbers in binary, speaking the chip's language. Before we can do all this complex math, we have to know how microprocessors actually view signed integers. Basically, there are 3 main ways to represent them. You've got signed magnitude, which devotes exactly 1 bit just to the sign. Then there's ones complement, which relies on bitwise complementation. But the undisputed star of the show, the one used natively by almost all microprocessors today, is 2's complement. Here, the negative value is represented by a specific complementation constant, 2 to the power of k.
And there's an absolutely essential rule when you're working with 2's complement, specifically regarding how we extend a number's digits if we suddenly need more precision. You can't just arbitrarily add zeros everywhere. To maintain the correct mathematical value, you have to replicate the sign bit from the left. This is called sign extension. And then you pad with zeros from the right. Doing this ensures the processor doesn't suddenly mistakenly think a negative number has magically become a massive positive one.
All right, Section 4, multiplication and scaling, the math tricks.
Let's move to and see how this builds using a really relatable base 10 example. Imagine your hardware can only multiply whole integers, but you desperately need to multiply 0.7 by 0.6. Well, step 1, the programmer promotes those fractions to integers. You multiply by 10 to get 7 and 6. Step 2, the hardware simply does what it's built to do. It multiplies 7 by 6 to give you 42. And then step 3, you, the programmer, remember that scaling by 10 twice means the product was scaled by 100, so you mentally shift the decimal point back to get 0.42. It's basically a bunch of mental gymnastics just to avoid buying a more expensive chip. Now, this exact same concept applies directly to base 2 binary math inside the chip. But instead of multiplying by powers of 10, we promote using powers of 2. For instance, If you want to represent 2.7, you might multiply it by 2 to the power of 6. That gives you 172.8, which we then just round to the integer 173. We feed that 173 straight to the hardware. The hardware multiplies it, and the programmer diligently tracks that product's scale factor so the binary point can be accurately placed later on.
But hey, multiplication is really only half the battle. What happens when we need to add things together? A classic example of this is computing an FIR filter, where you're accumulating multiple multiplications. The absolute golden rule here is this: you cannot add numbers with non-aligned binary points. I mean it. If one number has a scale factor of 2 to the 8th and another has a scale factor of 2 to the 9th, adding their raw integer values together will literally just yield complete gibberish.
Let's look at a real-world example from the source material to clear this up. Say after our first filter multiplication, we end up with this raw hexadecimal value, 373H. Now, we as the programmers know this carries a scale factor of 2 to the power of 8.
Now let's say our second multiplication resulted in a completely different value, and this one has a scale factor of 2 to the power of 9. To add them safely, we have to align the decimal point. We do this by taking the second value and right-shifting it by 1. This essentially divides its scale factor to perfectly match 2 to the 8th. The raw hardware value then becomes 138H. Now, and literally only now can the integer hardware safely add these two hexadecimal numbers together.
So the absolutely crucial takeaway here is understanding normalization. When you add two numbers, you might generate what's called a carryout bit, which requires an extra bit of precision. To squeeze the result back into your set variable size, let's say a 10-bit integer, you have to right-shift the sum. Now, in floating-point hardware, this normalization and tracking of the scale factor happens automatically, right on the fly. But in fixed-point arithmetic, you do this right-shift manually, every single time, keeping the scale factor completely constant and predictable.
Finally, Section 5, the rounding problem, the messy real-world caveats.
The absolute simplest way to drop fractional bits is truncation. Just chopping them off. But chopping has some pretty severe flaws. Because of how 2's complement works, chopping always reduces the value of the number. It generates massive errors ranging from 0 to almost 1. And worst of all, it creates a biased asymmetrical approximation because the error range isn't symmetrical around 0. Over millions of calculations, this bias will drastically skew your final results. It's a real problem. So ideally, we want to round to the nearest value, where 0.5 naturally rounds up. You might be thinking, well, let's just write an if-else statement in our code. Actually, scratch that, because in embedded systems, branches from an if statement can cost 5 expensive clock cycles. Instead, engineers use a brilliant branchless round to nearest trick. Step 1, simply add 0.5, which is 0.1000 in binary, to your number. Step 2, right shift by 1 to drop the fractional bits. Addition and shifting only take 1 cycle each. It is incredibly cheap, it's super fast, and it achieves perfect rounding to the nearest integer.
And this brilliantly illustrates a tiny flaw. Even rounding to the nearest integer is slightly biased. Notice that positive 3.5 rounds up to 4, but negative 3.5 rounds down to negative 3. The alternative is von Neumann rounding. With this method, if any dropped bits contain a 1, you forcefully set the least significant retained bit to a 1. I know, it sounds a little wild, but mathematically speaking, it's completely unbiased.
Which leads us to a fascinating mathematical cliffhanger. Truncation is biased. Round to nearest is biased. Von Neumann is unbiased, but it's pretty rough. So can we actually have a perfectly unbiased round to nearest scheme? Well, the answer lies in a complex technique called rounding to the nearest even number. It is incredibly difficult to implement without dedicated hardware, but it might just be the holy grail of fixed-point precision. Something to think about the next time you trust a tiny, cheap microchip inside your microwave to perfectly calculate the math.